Hello, everyone. Thank you for joining this week's webinar. We're excited to talk about fine-tuning DeepSeek and reinforcement learning. There is a ton of content to go through today, so we're just going to start jumping right in. I see folks trickling in, but the train is leaving the station. Travis, could you put the next slide on, please? Quick logistics. You'll see all lines are muted. So I'm going to be turning on the chat right now. So anyone, please go ahead and put it in the chat where you're dialing in from. We love seeing how far the global audience comes from. So say hello, please. The session is going to be recorded, and we'll be sharing it in the next few days so that you can watch it later or share it with all your friends. I'm going to be launching a quick poll also in just a moment. Please answer these polls. They really help guide our content calendar to make sure that we're giving you content that's really helpful for what you're trying to build. And you'll see at the bottom of your screen, there's a Q&A panel. Please ask any questions through the Q&A because things get lost in the chat. So questions for Q&A. And we have a free trial, so you can go to this link to get started with $25 in free credits. And we'll be posting more about that through the chat as we go. But that's, I'll leave it there. I still see some folks trickling in, but I'm going to turn it to Travis now to kick us off. Thank you.
All right. Thanks, Will, and thanks everyone for joining us today. Quick run through of the agenda. As Will said, we've got a lot of stuff to talk about, so try to get through everything as quick as we can. First off, we're going to talk about the reason why we're here, which is the DeepSeek-R1 model. Why are we talking about it specifically? What's different about it? What new techniques have they brought to the table that are worth mentioning? And then we'll also talk about the idea of how you fine-tune models like DeepSeek-R1 through different techniques, including reinforcement fine-tuning and supervised fine-tuning, kind of compare and contrast these approaches, show you some of our experimental results. And then I think most interestingly, Arnav is going to walk through a case study, specifically one focused on a problem that we think is actually quite interesting for us anyway, which is how you can auto-generate CUDA kernels from PyTorch functions, show you how we did that, the lessons we learned, and then finally talk a little bit about how we're building this into a self-service experience in our product in Predibase, and how you can and how that's being informed by a lot of the work that we've done to date, to figure out like what tooling is really needed to get the best results from this kind of approach. So let's start with DeepSeek-R1. By now, I think most people have probably seen this graphic. This was, I think, the big splashy thing that got people excited about initially, is that, hey, this was the first time that we've seen an open source, truly open source model, MIT licensed, come out that was really competitive with what was the state-of-the-art model, O1 at the time. And that was just coming off the heels of just a few months after O1 was released. And so, the lesson there was, wow, this is like a really powerful model that can be used for real-world applications. Maybe, this is the moment where open source is finally going to, catch up or surpass the proprietary models. And one thing in particular that makes R1 different from a lot of previous generation models is that it's also what we call a reasoning model, right? And specifically, when you look at the prompt of how they fine-tune these models, you'll see that they specifically call out that they want the model to, think and explain its reasoning process, and then finally provide an answer at the end. And this kind of technique of getting the model to specifically talk through its reasoning as it's kind of generating these reasoning tokens, is also a technique that's been around for a while called chain of thought, but now being encoded into the model through the fine-tuning process itself, so that natively speaks in this kind of verbose, step-by-step way. And the reason why people do this is because it helps solve problems that are not very straightforward, right? It's like oftentimes for math problems, for example, you'll see that if the LLM is just told, just give me an answer, it'll try to give you an answer, but it won't necessarily be correct. Whereas if it's able to break down the problem one step at a time, maybe sum a couple things together and then arrive at the final answer, it can get much higher accuracy. And so this kind of idea of breaking problems down into incremental steps is really at the heart of both chain of thought and how models like R1 work under the hood. Now, one thing I want to call is that DeepSeek-R1 is not actually just one model. They trained several different models. And this was one graphic that someone on X put together, kind of trying to show how it all fits together. But you can think of the core R1 model, this was the big 600 plus billion parameter model they released, as being trained from a very complex process where they started with their existing open source DeepSeek v3 model. They created this cold start fine tuning data, did some reinforcement learning, did rejection sampling to retain only the best samples from that set, and then did final supervised fine tuning on the final set, and that's where they arrived with R1. They also trained a set of distilled models. So these were models that were smaller SLMs like Quinn, et cetera, from that same training data set that they used to train R1. And so a lot of folks, have probably played around with these, and we currently host, the Quinn models, for example, in our platform to try out. But I think one that's really interesting that doesn't get talked about enough is this third model here, which is R10. And what's really interesting about this is that you notice that the training process is way simpler, right? It's like there's none of this, supervised fine tuning and, reasoning data, rejection sampling. It's just take the original DeepSeek v3 base, do some reinforcement learning on it through a technique called GRPO, and then finally you get a model out the other side. And we'll come back to this specifically once we talk about fine-tuning techniques for these models. But this is really, I think, a very novel thing that came out of this whole work. Now, the GRPO algorithm itself that they use to train R10 is also kind of simple at the end of the day. It's a simplification of a well-established reinforcement learning algorithm called PPO, where instead of having this separate value model that tries to assign the kind of relative rewards, et cetera, you have this concept of, well, what if we just had the current version of the model generate a bunch of different candidate completions, and then using a scoring system or a reward model, we determine what the relative value or advantages of each of these individual completions is. And then based on which ones do well, we try to tune the model to do more things like that. And then which ones do poorly on the reward function, we try to discourage the model from producing generations like that. And the reason why this was, particularly interesting is that it kind of just works. There's not a whole lot of hyperparameter tuning you have to do in the way that you normally would for PPO. And it also has a much lower memory footprint. So it's more accessible to commodity GPUs and not having to train on huge training clusters. And when they ran this technique on, the sample data, what they realized was that the model started to learn advanced reasoning strategies organically without having to be explicitly directed in that way. And they called this the aha moment in the paper. And so you can see, when you look at its reasoning process here, it's trying to solve this math problem. And then it gets to this point and it says, wait a minute, here's something important. I can flag this. And what's really crucial to point out is that they didn't actually teach the model to do this. It just kind of learned to do it itself, right? And this idea that these models can emergently develop these novel strategies is something that, we've seen shades of in the past with different, reinforcement learning strategies like, with AlphaZero and things like that, but never really in the context of LLM fine-tuning and chain of thought. And so this was really like a novel discovery that came out of this. And maybe last but not least, I'll just say that this, R10 model, while it wasn't, as strong as the R1 model itself, which was a much more complex training procedure, it was actually very strong. It actually beat O1 Mini on a number of benchmarks across the board, and then, was slightly worse on a couple. And then even the O1 model itself, it was competitive with and actually beat in a few cases. So, this was a very powerful model that was trained with a very simple fine-tuning strategy based on reinforcement learning. And that brings us to the idea of reinforcement learning as an alternative to traditional supervised fine-tuning, which is, kind of the main topic of discussion that we want to get into here. So one question you might have after seeing the success of DeepSeek is, okay, this is really cool. Now, how do I fine-tune a reasoning model like DeepSeek to perform better on my specific tasks, right? This is a question that we've thought about a lot at Predibase even before reasoning models, but now is even more important now that we have these really powerful open source models available to us. Now, traditionally, we do use a technique called supervised fine-tuning to train models for fine-tuning. And this is what we call an offline training process. Usually starts with a static data set of here's some example inputs, here's what you should output. There's a frozen LLM backbone with a trainable LoRa layer, if you're doing parameter efficient fine tuning, then out the other side, you get a final checkpoint, and then you serve that with an inference server like Lorax to be able to get fast inference in production. And this works in general for a lot of tasks, particularly tasks where the right answer is just a single number or classification task or something like that. Even text can work with supervised fine tuning, provided that you just want it to essentially mimic whatever is in the training data. Like if the training data is the right answer always, and it's objective, then supervised fine tuning is a good way to go. But for these reasoning models, you have an additional complication, which is you don't just have to think about the model generating a final answer. You also have to think about what reasoning you want it to generate. And this is important because if you fine tune a reasoning model to just generate the right answer without the reasoning, it's going to essentially regress and forget how to do reasoning and just spit out a final answer. So you kind of lose the whole point of the reasoning model in the first place. So you need to provide this reasoning data during the fine-tuning process for doing supervised fine-tuning. And then that leads you to the question, well, how do I actually get good reasoning data in the first place? So one technique that you can use is called reasoning distillation. This was also a technique that they used in the R1 process for training R1 and also the R1 distillations, where you take a supervised fine-tuning data set like the one we showed previously, and then you ask a strong reasoning model like R1 to generate a bunch of different candidate solutions to each question, including the reasoning traces. And then you use a technique called rejection sampling to basically say, only to keep the ones that are correct and the ones where the reasoning looks good based on some heuristics or based on LM as a judge. That gives you a final golden data set from which you can then do normal supervised fine tuning and get a fine-tuned model out the other side. And this works, but it does have some big limitations. One is that you typically need very large amounts of data for it to be effective. This was what they saw in the DeepSeek work, where they had 800K examples that they were fine-tuning on. Otherwise, you can end up in situations where it's just very high loss, very hard to get them all to converge and generalize across all that reasoning data. There is some recent work from a particular paper called S1 that showed you can get this kind of effect with as little as 1K examples, but crucially, those 1K examples were very, very highly refined and hand curated for lots of different properties. And so, one way or the other, you're going to have to do a lot of work to get a good data set to do this. And then last, also, you're capped by the performance in a big way by the quality of the teacher model, right? Like you're not able to explore new strategies or discover new solutions to hard problems. It's like at the end of the day, the best you're going to do is be able to get the smaller model to do as well as the teacher model. Because you're ultimately training on that reasoning. You're not letting it explore the reasoning space organically. And so that brings us to an alternative, which is reinforcement fine-tuning, also known as reinforcement learning with verifiable rewards. The reinforcement fine-tuning is a name coined by OpenAI kind of late last year that's kind of stuck. And the idea is very similar to the process that was used by DeepSeek for training their R10 model, where you have a data set, you have this trainer using a method like GRPO. It's spitting out checkpoints periodically. Those checkpoints are loaded dynamically into a multi-layer inference server like Lorax. Lorax is then generating multiple different candidate solutions to every input prompt. You have a separate reward server that's scoring those completions. And then based on those scores, we update the model online and then repeat. So the model is constantly able to refine its suggestions. It's constantly able to try new things, see what the score is that comes out the other side, and then iterate on that. And the benefits of RFT is that you don't actually need labeled data for this process to work. The rewards function, the rewards server rather, just needs a way to verify correctness and score those outputs. It can work effectively with as few as 10 examples, and we'll show you a bit more about that in the case study that follows. And it also enables reasoning models to organically discover better strategies rather than just being beholden to one particular strategy from a teacher model. And this is kind of coming back to that aha moment that DeepSeek R10 talked about, is you can rediscover that yourself using techniques like this. And without getting the details too much on some of these specific examples of data sets we explored, you can read our blog post for more information on that. But the TLDR there is that for certain tasks, specifically like these mathematical reasoning problems or puzzle games like Countdown, RFT just blows SFT out of the water. SFT is not able to adequately generalize even with thousands of examples, whereas RFT is able to improve not just on the base model, but even base model with chain of thought by a significant percentage. And then this also kind of coming back to this, how many training examples do you need for this to be effective point? You can see that even with as few as 10 examples, RFT was able to find some good generalization. So it was able to avoid just like memorizing that training data and was able to demonstrate significant improvement over the base model, even with chain of thought. Now, important to note that this doesn't apply universally to every data set. There's another data set we explored called Logic QA. It's like a logical reasoning, multiple choice quiz type data set. And you can see that in this case, SFT actually did end up outperforming RFT at higher quantities of data. But one thing I also want to point out is that even in this case, where this particular problem was just well suited to SFT, it turned out that with small amounts of data, like that 10 example size data, we still saw the same effect where RFT boosted performance over the base model. And crucially, SFT actually broke down here. It started to overfit and memorize and not learn any general patterns. And I think this is one kind of key takeaway that you can carry with you, which is, if you have small amounts of data, SFT is usually not going to do very well, but RFT can actually be beneficial even in those cases, and even for problems where RFT is not necessarily the optimal solution when you have large amounts of data. And so just to wrap on this, here's kind of a quick breakdown of how we think about the decision framework for whether you should use SFT or RFT or something else. And as with most things in fine tuning, it starts with the data. So the first question that we would ask is, do you have labeled or ground truth data that the model can learn from? If you don't, then the next question we'd ask is this task verifiable? By which we mean, is there some objective and an automatic way that you can determine whether a particular answer is correct or incorrect? And you can think of like, compiling source code as an example of this. Like you might not have the label that says this is the right piece of source code to generate for this particular input, but you might have a way of compiling that code, and you might have a way of running test cases against that code, and that can be the verification process, right? So if you do have a verification process, RFT can still be a good fit. You just need inputs and a verifier. You don't necessarily need ground truth labeled data. If you don't, then you're starting to get in the realm of what we call reinforcement learning through human feedback, where you're starting to think more about things like human preferences and subjective tasks, where techniques like DPO might be useful if you're familiar with that. So that's like a whole nother class of problems that's more about getting models to generate different output that aligns a little bit better with subjective preferences. If you do have labeled data, then the first question is, how much of it do you have? And if you don't have a lot, if you're in that kind of 10 to 100 data point examples regime, then definitely RFT is, again, a really good fit, even independent of the problem type itself. We find that it performs better than SFT in those cases. If you have lots and lots of data, hundreds of thousands of examples, this is an area where where SFT starts to become more and more practical. Obviously, with R10, they were able to do this even with, hundreds of thousands of examples, but it was very expensive, right? And so it's worth bearing in mind that RFT is slower than SFT. So if you have huge amounts of data, you might be better off doing SFT in those cases. But if you're in that middle range, you have thousands of examples, maybe tens of thousands, then I think the next most important question to ask is this really a chain of thought kind of problem? Is this one where if I take the base model, prompt it directly, and then I prompt it with chain of thought, do I see some lift even before doing fine tuning? And if the answer is yes, then this is also a really good candidate for RFT because you can fine tune a reasoning model like DeepSeek-R1 or one of its distillations and get that boost in performance by improving the reasoning itself. Whereas if reasoning doesn't really help, as we saw with the logic QA task, this is again another case where good old-fashioned SFT can actually be the right way to go. So that's my section of the slides. I'll go ahead and pause here to quickly tell you about our early access program to RFT. So, you might be asking, this is kind of interesting. How do I try it out? I think, we talked a little bit about use cases that are good fits. So here's the QR code if you want to check it out and talk with us about getting early access. But with that, I will go ahead and hand things over to my colleague Arnav, who will be talking a little bit more about a specific use case and case study that we explored, applying RFT to a real world problem.
Thanks, Travis. Let me quickly share my screen. Uh, Let me see. Why? Okay, can everyone see my screen? I think yes, right? Perfect. Cool. So, yeah, what we're going to do now is actually try and apply some of the ideas that Travis was talking about earlier in terms of reinforcement fine-tuning, reward verification, and actually see how that works, and I saw a lot of questions in the chat about, what are the differences between reward modeling and how do you actually verify the outputs are correct? So I'm hoping that as we work through this case study, piece by piece, it'll become very obvious, how you can formulate, reinforcement learning style ideas through this GRPO algorithm that DeepSeek came out with. Cool. So to set some context, right, the goal we're trying to solve for today is, can we teach an LLM how to convert PyTorch code, right, into functional, accurate, and optimized Triton or CUDA kernels? Now, for those who aren't familiar with what CUDA kernels are, CUDA kernels are essentially functions that are purpose-built to run on GPUs. And the reason that they're very interesting is that they can run many small computations in parallel all at once and then combine the results or some combination of that. And usually these are really, really fast to run on GPUs compared to, doing something that's not so optimized. And CUDA kernels are typically written in something called like CUDA C or CUDA C++, which is extremely low level. So for people who work in, as data scientists or machine learning engineers, unless you have deep expertise, it's a pretty difficult problem, write yourself. And so there's an alternate called Triton. Triton is essentially a compiler that is able to compile down to CUDA C and CUDA C++ for you. But the really nice thing about Triton is that it's actually written in Python. So it has a Python API. You can express that logic of GPU programming in something that you're comfortable with, and leave it to Triton to compile it down into something that can run on CUDA. Right, that's the high level idea. And I'll show you what that looks like in a moment. But the reason this use case is very interesting is that, there are many cases where you might want to transpile code between, convert Java to Python or Python to C, C++, right, like this. Or there are other use cases like an enterprise where, we've seen a lot of people and a lot of companies that have, natural language to code generation for some sort of workflow, things like that. And so a similar formula can be applied for those tasks as well. Now, to show you what this looks like in practice, right, here's an example of a simple two-line PyTorch function, or a function that uses torch, and it's called silu in place. And all it's doing is it's computing the silu activation function on a tensor in place, which is a very common operation in deep learning these days, especially in large language models. I won't dive into what's actually happening in the torch function, but what you can imagine is we have this piece of torch code. We want to give it to an LLM, and we want the LLM to generate this large blob of output code. And what this code is, so this code actually represents a Triton kernel that is functionally equivalent to the PyTorch code on the left, but it is significantly faster in its execution, right? And you can see that, I know that most of us here are not GPU programming experts. Maybe have never heard of Triton, maybe have never heard of CUDA kernels. So we don't need to focus on the specific details, but I think that the point I'm trying to get at is that it's a pretty challenging task to get right, even for humans who are experts in the field, let alone an LLM. Now, as I alluded to earlier, writing CUDA kernels requires deep GPU programming expertise. There's people who spend lots of time writing these kinds of things. And uh, the interesting challenge about this is that most people know how to write things at the level of Python, at the level of PyTorch. But when you execute PyTorch code by itself, it's often suboptimal. And so you're wasting GPU resources. So it makes sense to actually have a way to write these optimized CUDA kernels. And so, that's one of the challenges with this task. And the second is that, why it becomes interesting is that when you move to different pieces of hardware, so H100, H200s, like the GH200s when they come out, or I think they're already out, a lot of these kernels, like each of these have different GPU architectures. And so you want to write kernels that are leveraging the hardware characteristics, and, hand optimizing these each time is time consuming and error prone. So would be pretty nice to just have PyTorch code and then send it to an environment and have it learn how to optimize it for that architecture, right? So yeah, that's like the high level idea. And what I did want to emphasize is like, normally when I see tasks like this, I think about supervised fine tuning, which is what Travis was talking about earlier. It should be a good fit for a task like this, but unfortunately, one of the most interesting problems is that there is no open data set for a task like this, even though people are interested in it. And so, supervised fine tuning is unlikely to work well because we don't have enough data. And so that's actually where, a task like this is now possible through this new idea of reinforcement fine tuning. And here's why actually this task in particular is a really good fit. The first is that we obviously lack a large data set and one that has input and output pairs, so it's labeled. But with reinforcement learning, because it's an online algorithm, I'll show you what that means in a moment. You can essentially just hand curate 10 examples by yourself and create a data set out of that. And that is enough to get started, right? Very, very simple. The second is that because we're writing code, code is inherently verifiable, right? And it's objectively verifiable, and that code always executes the same way most of the time, right? And in our case, what this means is that we could have something write kernels and then maybe write something like test cases, run it against the code and see if it compiles and produces the same output. So we have a mechanism that we can devise to basically grade the quality of the output that the model is producing. And the third is that, large search spaces, this problem is like, it has many different solutions because you can go all the way from getting it correct to optimizing different parts and, for different matrix sizes. And there are analytical solutions, but it requires very deep expertise. But reinforcement learning balances this idea of exploration, which is what are the different things I can do with exploitation, which is what is consistently working really well. And reinforcement learning should be able to explore the search space in a very smart and efficient way compared to, how we might do it. So all of these make it like a really good setup for reinforcement fine tuning. So hopefully the problem statement is clear and people know what we're trying to solve for. So let's dive into methodology and learnings. So when you're constructing a problem like this and you want to run it through reinforcement fine tuning with GRPO, the DeepSeek formula, there are two key components you need to construct: a data set, at the very least, with some prompts. And the second, and these prompts, ideally they're well structured, there's a bit of diversity, but what you're really looking for is very high quality inputs, right? Just 10 is sufficient. And some sort of diversity so the model can learn a generalized strategy to solving your problem. And the second part is the verifiable deterministic reward functions. And I know people have many questions about this, and I'll show you what it looks like 2 slides from now. But the idea is that, since you don't have a ground truth to compare to, you need a way to at least tell the model in some capacity whether it's doing something correctly or not. And you want to be able to do that in a very objective way so that every time the same output is produced, you give it the same score and there's no non-determinism. So it knows for a fact that this is like the score it's going to get. And by keeping it objective, we eliminate noise, should help train the model faster. So let's talk about how we would create a data set for this task, because that's what we had to do, right? So when it comes to data set creation, here's the easiest strategy that you can think of for a task like this. This is what we did. We went to GitHub, a treasure trove for open source code that lives out there. And we searched through a bunch of open source repositories that have some sort of Triton kernel implementations. And there are actually quite a few that have, people practicing, just like how to write Triton kernels, to people actually like using Triton kernels for their specialized tasks, so on and so forth. And what you can do is you can actually like grab these kernels out from these code repositories that are open source, and you can run them. And what's really nice is that most of the times people write like a PyTorch equivalent and then a kernel equivalent, and then write a test case to show that the output is the same. So you can verify that it compiles and the kernel is valid. Now, once you have that, remember, this is actually sort of like the output, right? But what we want is an input we can pass to the model to actually generate these kernels. So what you can do is one of two things from there. I did like mostly the first, which is convert the Triton kernels to Torch code yourself. Or if they have torch code in these repositories for these kernels, then copy them over, fix them, modify them to make it make sense. But if you're not an expert, we can always send it to, let's say, like Llama 370 billion and have it generate the PyTorch code for you, and then you can modify and fix it as you want. And then finally, to make sure that our Torch code is correct and our Triton code is correct, we can write some test cases, run it through both, and validate that all test cases pass through both. So we know the Torch code is equivalent to the Triton code. And what's really nice about doing it this way is that your test cases can also be used during training to verify correctness. And we'll come to that and I'll show you what that looks like as well. So our training set is just 13, I want to be clear, like 13 examples that have like a system message and this PyTorch code. I showed you a snippet in the first slide. And the goal is basically to tell the model to write, equivalent Triton kernel. So now that we have our data set sort of handcrafted this way, it only took me like 30 minutes or so to get this there, or maybe an hour. The second part is, how do we now write verifiable deterministic reward functions? And a really good framework to think about reward functions is you want to do two things. So the first is that, and DeepSeek also kind of followed this formula, and it's very understandable why now. So the first is that you want to write a formatting reward function, and the idea is that you want to do two things with it. The first is give it some knowledge on, what a good solution might contain. And the second is give it some sort of format so that you can extract out the answer and then verify it, right? If it's very open-ended, you don't know what part of the generation to look at to verify. But if you tell it like, hey, put your answer between answer tags or put your answer between code tags, then you can look for that in the output, extract it out, and then verify correctness. So the first is the format reward function. And the second thing you want is a correctness reward function, which is actually telling it like, hey, was this answer correct? Yes or no. So in our case, when we first took a stab at this problem, we decided to go with 3 reward functions, 2 for formatting and 1 for correctness. So this is an example of a reward function. And as I said, there's 2 interesting properties about it. It is deterministic, deterministic, programmable, and verifiable. So what I mean by that is for each generation that the model produces for a given prompt, we can say, hey, do you have the Triton code / Triton code tags present in the output, right? And that's done through this like regex match written over here. So we take the completion, do regex match, and say, if you have 1 instance of this exactly, then great, you get a reward of 1. Otherwise, you get a reward of 0, right? So the idea is that over time, it will probably try to produce these tags, and we'll tell it to do that in the system message. And whenever it does actually produce this, we'll say, you did well, like here, you get a reward of 1, others you get a reward of 0. And this is what we're going to look for to extract our code out to then execute it later, right? So we wanted to learn this pretty quickly. The second is a Triton keyword reward function. Just very simple. It's almost trivial. I'm checking if it's just importing the right Triton packages, because we know that is the first set of lines that are required to actually write a valid Triton kernel that will execute. And so it just does string matching, like is Triton.jit in completion, import Triton in completion, or import Triton language STL in completion. And if all 3 are true, which are required, then you give it a reward of 1, else you give it a reward of 0, right? And again, hopefully during its early exploration phase, it will try this by itself and get those rewards and then use that as signal to do this continuously. So these are 2 format reward functions that we wanted to learn. And then the third thing, as I mentioned, is the correctness reward function, right? And it was a lot of code, so I didn't put it here. But this is sort of like a flow chart that describes what's going on. So for each completion, we follow like a multi-step process. We say, hey, are there Triton code and / Triton code tags present? If not, we return 0. But if yes, we can extract that code out from those 2 tags, right, using regex matching. And then we check, hey, do you have an entry point function, basically a regular PyTorch function that we can call and pass in the test case values? And does that invoke a kernel call internally? Yes or no, right? And you can do that by loading the code into a module and doing some interesting massaging and parsing. So if it doesn't have that, then we know that this cannot be a valid kernel to begin with, because those are the two things we want it to do. Let's say it gets that right as well. The third step is to load this code, right? We know it's valid, run the test case in a new Python interpreter on a GPU, and then capture the output value. Now, two things might happen here, three things really, right? It might throw an exception, which means that, there's a compile time error or a runtime error because Triton kernels are just-in-time compiled, in which case it will return an error of 0. But in case it doesn't throw an error, it might either get the answer correct or wrong. So if it gets it correct, it will return a reward of 1. Otherwise, it will return a reward of 0, right? So it's a very simple way of verifying, right, that it's learning something and that it's doing the right thing. And this is an example of like a correctness reward function. So this is what we took a stab with and kicked off training. And oh yeah, sorry, I should probably also talk about system and user messages. So how does it know to produce these like Triton code tags, or hey, like make sure you have, an entry point function and a kernel function? You actually use your system message and your user message to tell it that. And so, here's an example of like our system message and our user message initially. You'll notice that there's no think tags here. It turns out that this model doesn't need to think to do this task. In fact, it gets worse when it thinks, and that happens sometimes. It's just task dependent. But yeah, just wanted to show you that there's something like this. So with all of this, we can kickstart our reinforcement fine-tuning training loop. And, we start with our frozen model. We take a prompt, right? We send it to Lorax, which is our open source serving framework. And we have it generate n different completions for the same prompt. And this is done with temperature-based sampling so that there's some difference between each prompt that's produced. We pass those to a reward server, and the reward server takes the completions and produces rewards from each of the reward functions for every single generation, right? So format is scored separately from the Triton formatting, which is scored separately from correctness, and those scores are sent back to the model server. The model server looks at that, calculates something called advantages, which is which generations were better than the average and which generations were worse than the average. And then the weights are updated. So your LoRa weights, we use LoRa-based fine-tuning. It updates the weights. And then what we can do is send this new checkpoint to Lorax again and say, hey, here's the next prompt. Can you generate n more completions? So it's this online learning process where you're utilizing the latest model every single time. And we loop over, 13 data points over and over and over again in this fashion. And here are some of our initial observations. So what I have here is like 3 different sets of learning curves. There's the rewards, the format reward function on the top left, the Triton format reward function on the top right, and then the correctness reward function on the bottom left. And there's 3 observations we can make from looking at this. The first is that by training step 100, both the formatting reward functions actually have, are nearly right 90% of the times in all the generations they produce. That means that it's actually learned to produce our formatting quite well by this point, which is great, right? It's a sign of learning. Like it is learning how to get it through trial and error to exploration. The second is as we approach the 100th step where formatting is finally correct, you'll notice that there's a pretty steady increase in the frequency of getting the correctness right of our test cases. And that makes sense, right? Now you have all the right imports, you were able to parse out the code clearly, and it's learned how to do that for all of our examples pretty well. And so now it's able to actually run our test cases through, and it's learned over time through trial and error what at least, compiles and can run without errors. And then, yeah, sometimes it gets a lot of things right. So you'll see these spikes, which basically said got both of our test cases right. So it's an emergent property that comes as part of like the training process over time. And the third is very interesting too, which is that the correctness reward takes much longer to learn than the formatting rewards. But I will say it is actually learning faster than I expected, because on our test set, it produced a score of 0 out of the box. So it should take much longer to learn how to get it right. And so the question then is that it? Does that just work? Do we just let it train and does it get everything right over time? Maybe. We should also look at, individual outputs that are being generated and assess whether it's doing the right thing, right? So again, there's a lot of code and text on the screen. We don't have to focus too much on it. But what I wanted to show you is on the left is the Triton kernel that was actually generated by this model. And on the right is the ground truth Triton kernel that I got from GitHub. And you'll see that functionally, they're almost exactly the same. Just some edge case handling that's missing in terms of like how you write and read from memory. So great science, looking pretty good. But the more time we spent with these generations, it became obvious that it's not always so good. So here's another example where on the left, it's a summation kernel, just sum along dimension 1 in a tensor, produced by the model, and on the right is the ground truth. And one really funny emergent property of reward functions like this is that it can lead to something called reward hacking. So this kernel is actually completely wrong. And it's wrong. It's wrong in that it actually gets 100% of the test cases right, but it does it because it found a clever loophole to our reward functions. What it's doing, in a sense, is no matter what's happening in the kernel, at the end, it calls x.sumdim equals 1, which is just the PyTorch implementation that always works. So it basically wrote a dummy kernel function that does nothing, but it found a way to maximize reward anyway. And this is actually a very common phenomenon in reinforcement learning, where the model comes up with a very clever way to work around the reward functions to maximize it. And so, this is an example of an undesirable behavior because this effectively doesn't do anything, but it passes and gets maximum reward. And so as we analyze this further and further, here's an example of what's supposed to happen, but we can skip past it. There are other emergent challenges. I saw that it keeps invoking invalid Triton methods or, tries to load them from the wrong library. It learned how to exploit test cases where the output is just a tensor with zeros because it just skipped the kernel call and just returned like torch.zeros. Very clever. And in our rewards, if you see how we define those, they were all either you get a score of 1 or a score of 0, right? So you don't provide any partial credit for partially correct outputs. If it compiles, it should get some signal that it's made progress, but we only tell it it's doing something at the end when it gets something right or wrong. So learning is slower and it can go a bit more rogue in its exploration because of that. And that's called like having reward signals that are too sparse. And yeah, having only 2 test cases means that the reward signal is also very sparse, and I'll talk about that a bit more in a couple of slides. So from this first pass, we can see that it's directionally doing something. It's showing promise, but it's obviously not nearly where we want it to be. So in general, reinforcement learning with this style of strategy with GRPO is sort of iterative in that you need to look at the reward curves, look at your reward functions, and look at what the model's generating, and based on that, make changes and keep improving your reward functions. And so we wanted to solve for all of these challenges as well, and we went through several iterations. So I'm going to show you what we came up with in the final iteration now. We did this over a week. The first is that we use a much more comprehensive system message. The first thing we did is added an explicit sort of like part of the system message that tells it all the valid functions in the Triton.language module so that it hallucinates less in producing invalid functions. The second is telling it how exactly to invoke these functions. So you can do like tl.method name, and that will work. But it doesn't know what arguments get sent into the function. It just knows this function exists, right? So kept it simple. And the third thing is we want to solve for reward hacking, and I'll tell you like the actual process. But we tell it that the output buffer, like the place where it should generate the output from the kernel, should be the first argument it sends to the kernel and be called output. And this is the artificial format that we are enforcing so that we can verify that it's doing the right thing, right? And I tell it like, hey, use torch.zeros or torch.full specifically to initialize these buffers for specific reasons. So updated system message, giving it even more context clues because it's struggling to get it right, or it tries to hack it without these, which is totally possible. The second is actually improving the format reward function. So we're going to do like a couple of different things. We're going to, one, merge our 2 format reward functions into one. The second is that we're going to expand the list of reward criteria by being even more specific about what is good and what is bad based on our learning so far. The third is that, so let me show you what that looks like. Are the Triton code types present? Does it use the imports? Does it use only valid methods from the Triton language library? Does it use torch.empty? Does it use load and stores properly? Some other signs that, it's using the kernels the right way or setting them up correctly. And the third thing is, yeah, we can assign partial credit. So the idea is that as you expand the list of criteria, right, for it to get a score of 1, it has to get everything right if you just have binary reward scores. The odds of it getting that is very low, right? It's going to have to like luck out and get all of those things correct. So it doesn't have much signal to learn like what to try next. But by giving it partial credit in this fine-grained way, it knows that this is slightly better than this, and this is slightly better than this. And it can use those increments to head towards the right direction where it gets all of these things correct. And the second thing is we can also introduce negative rewards. Like, hey, we want to discourage this behavior. So if you're doing all of this right, but this wrong, I don't want to give you full score because it's a behavior I don't want you to do. So that is also something you can do as well. And we found that this actually helps push it towards the right behavior that we want. And then you sum these and you get a total reward, and you do this per completion. So it's still very fast and cheap to do. It's just, string matching really, or regex matching, pretty fast. So much more expanded reward function. And then there's a much more expanded correctness reward function. And I know there's a lot of text on the screen, but what I want you to focus on is the 2 dotted arrows, or right here. This is the original reward function that we wrote. But what we want to solve for is checking for reward hacking. And the easiest way to do that is to, once your kernel, so the model produces a kernel, we ran it through a test case, and it produced a value. And it looks like the value was matching what we want, the expected output. To make sure that the kernel is actually responsible for doing the logic, what we can do is that we can monkey patch the actual kernel the model produced with the artificial no-op kernel that does nothing, right? And then we can check the output from that call. And what we would hope is that if the outputs match, then it's a bad sign, because it means that the function that's not the kernel is doing all the work, like we saw in that example with the reward hacking. So that's actually bad, and we want to give it a score of 0. But when the outputs differ between when we use the kernel and when we use the no-op kernel, it means that the score was entirely produced by the kernel, which is a great sign. That means it's doing all the logic using pure Triton. And for that, we're going to give it a reward of 1. So it's a special guardrail mechanism that we built to check for reward hacking, and you can use these ideas in other code examples as well. And the third thing is, as I mentioned, 2 test cases are rather sparse, right? When you have 2 test cases, it means you can only produce 3 reward values per generation. The score is 0, which means both test cases are wrong. The score is 0.5, which means 1 out of 2 test cases are right. And a score of 1, which means both test cases are right. But when you expand out the test cases to 4, you actually get much more fine-grained reward values, which again nudge the model in going towards the right direction, right? Instead of having more sparse values. Ideally, you would do 8, 12, 16, or 32 test cases, but obviously you need to spend the time to write those out, because that would give you much more continuous, less sparse reward. But for now, we just doubled our test cases from 2 to 4. And finally, if you're still with me, we also decided to give some partial credit for compilation, separate from correctness. And all it's doing is, hey, if you can run the code and it doesn't throw an error, you get a reward of 1, even if the output value is wrong, because it helps nudge it towards the right direction, given that the correctness reward is now much more complicated, right? So we want to give it some sort of intermediate value to use to go towards the right solution. So yes, to summarize, 3 things: much more improved and comprehensive format reward function. We update our correctness reward function to check for reward hacking. And we add a compilation reward function to give it partial credit when it can write functional code, even if it doesn't execute correctly. It doesn't produce the right answer at the end. And when we run it this way, we ran this for like 5,000 training steps, so much longer. There's, again, a couple of key observations that we can make, right, from doing it this way. The first is that we only start to see it getting 90% of the generations at, high success rate at 1,000 steps compared to 100. So it's spending a lot more time getting the formatting right, because it has to actually update its strategy to get there. And so yeah, definitely, like, the rules we enforced made it much harder for it to get formatting right, but it means that, it had to change the way it tries to greedily solve this problem, at least in my mind. The second is that, once we hit this 1,000th step, or when we start to approach it, you'll see that compilation reward starts to spike as well, right? This partial credit of like, hey, you wrote functional code that doesn't throw errors. But correctness reward basically stays 0 until, we start to see high format scores and high compilation scores, because at that point it starts to optimize for correctness and no longer for like compilation or reward functions. It finds that there's another way to maximize reward. And the third is that is correctness, which is, accuracy peaks at 2.5. Is that basically it goes through these like these variations where it starts to optimize for correctness, then it starts to optimize for compile, because it thinks that if it optimizes for compile, it will get higher correctness. And then we'll see at the at the tail end of the correctness reward function between step 4,000 and 5,000, it starts to spike up again. So, positive signs that it's learning something. And just to show you, again, we're not Triton experts here, but to show you examples of what this model actually produced, I'm going to highlight just a couple of quick things. It decided that it should add doc strings. To me, that's almost like its internal chain of thought to get to like a right solution. It correctly initializes the output buffer with the constraints that we have. It correctly like only passes an output to the kernel and returns the output directly. So it doesn't do any torch function invocation in this part of execution. And within the kernel itself, it does a lot of like really positive behaviors, which I won't get into, but like lots of good signs that it's doing the right thing. And these kernels are correct; they actually work. Similarly, here's another one to calculate outer product. Won't go too into it, but a lot of very similar signs. It learns, you can calculate block size ahead of time, use torch.zeros, just pass in the output and have the kernel do all the work. So it's a much more involved kernel because it operates on two 1D CUDA tensors, and yeah, gets it right as well. So it definitely like learns a lot more with these evolved reward functions. And there's obviously like things that to be done. When we ran this on the test set, now we're seeing like 40% accuracy, where it gets all test cases right on the test set, and then about 50% accuracy on 3 more of those examples, and on 3 it just gets it completely wrong. So what I want to highlight with that is that if you look at these curves, you can see that's roughly around 40% accurate. And that translates really nicely to the test set as well, because it doesn't know how to mimic. It learned the strategy for solving, which is what makes RL so powerful. And other things we can try next, scale up generations for faster convergence, increase the number of test cases to get even more granular rewards. And one thing we didn't optimize for is efficiency of the kernel, but you can imagine we can add a reward function for runtime where you run the torch code, you run the kernel, and you do like a distribution of time it took to execute. And then the bigger the difference between the torch and the kernel, the higher the reward, right? So you optimize then for not just writing correct kernels that get the right answer, but also using optimizing for efficiency as well. And that is something that it's verifiable and that it's correct and you know it's runtime. So lots of good stuff there. And with that, I know I have just a few minutes left. And we spent the past month working on this Triton to Torch to Triton use case, logic QA, countdown, and all of these other tasks. And we spent a lot of time figuring out, what are the pain points in getting this process working smoothly and nicely, what kind of tooling you need to actually make decisions quickly to help your models reach the performance that makes sense and that is very promising. And we decided to take all of those learnings and basically build it into our product, because we understand like where this process is difficult, and I think that's where really like I think for RL style training, managed solutions are going to be more attractive than ever. Right. So just to give you a glimpse of what that looks like in the product, or what it's going to look like in the coming weeks. Normally, when you land into the Predibase UI, we have both the UI and an SDK. You can pick between supervised fine-tuning and completion style fine-tuning. We're going to add a new task type called GRPO. And when you select that, you can pick, you can connect your data set to dropdowns, pick a base model. So you can use any of the DeepSeek models, but you can also use any of the non-reasoning models. This recipe works on those as well. Right, and you can configure trainer parameters such as epoch, learning rate, adapter rank, so on and so forth. Right, so lots of different things that you can do there. And when we train, we're going to show you these reward functions, like very similar to the ones I showed you. We show you on a per step basis, so you can see what it's learning and how each of those individual rewards are progressing, as well as the overall cumulative reward. And as you saw, it's very useful to see where it's struggling, what the trends are, and what the patterns are, because that gives you a lot of information. In addition to just seeing like the rewards, we're also going to let you see the completions being generated per step of training, which is actually incredibly helpful in seeing like what the model's finding as a strategy, like the aha moment that people talk about. They look at the generations themselves. Even we found our reward hacking through this. So you can filter to any of the prompts or pick a random prompt. You can look at all the generations for any given training step. And you can even, filter by a step to see how it's changed over time. Let's say like it's seen it for the 10th time. What is it doing now that it wasn't doing before? Which is incredibly powerful because we know that, this kind of information, like being live during the training process, can help you make really smart decisions about what needs to change. And in case you're more of a Python first person, don't really like a UI first experience, we also are building this into the SDK. And it's as simple as these many lines of code. So you can specify your base model, your trainer parameters, LoRa parameters, and then you can pass in a list of Python reward functions. And the idea here is that we want to let people customize how they assign reward so that they can train this for all sorts of tasks, which is sort of like a different approach compared to like the way OpenAI has been thinking about it. And you don't have to pass in reward functions. We will default to essentially doing exact matching and seeing if the exact matches are working. So this should give you full flexibility to actually reproduce our experiment with Torch, like the Torch of Triton, or Countdown or Logic QA, but also go really crazy with things like talking to a Notion, like it's a Notion connector and verifying like things there, or taking code, running it through your SQL database if you're doing text to SQL optimization. Yeah, basically the full-fledged, like you can design your reward functions as you desire, and we will execute them. And with that, once again, we are like, we have functional things that work, and we've run, hundreds of experiments at this point over the past month. And we have an early access program. We're happy to work with you to set up your reward functions, things of that nature. So your use case could be a good fit. Once again, if you don't have labeled data, but you can verify correctness, or you have some labeled data, but not a whole lot. And if, chain of thought prompting generally seems to help improve your model's performance compared to when you just, do zero shot inference without chain of thought. So yeah, with that, I'm at the end of my slides, and yeah, Travis and I are happy to take questions.
Thank you, Arnav. Thank you, Travis. We will try to run through a couple quick questions. We will not have time for all of them. We've been answering a lot through the chat. Please email support@predibase.com or find any of us on LinkedIn, and we can follow up afterwards also with more questions. Just looking at the chat real quick, let's see, pull in one or two real quick. Arnav, how important is determinism of the reward functions? Would the runtime reward, PyTorch runtime versus Triton runtime, be sufficiently deterministic?
Yes and no. So really good question. In general, I think determinism is extremely important because I think the DeepSeek paper suggests this as well, but non-deterministic reward functions are very easy to hack. And that usually means you're going to end up with a result that you don't want. You are absolutely right in that, doing runtime is technically non-deterministic, right? It's not like always going to lead to the exact same result. But my hope is that if you run it for enough iterations, let's say you take your test case, you run it, let's say 64 times, and then take the mean or the median time, that's a good enough representation, assuming the standard deviation is not very big. So certainly, like that's one reason we also didn't include it in the first round of experiments for this task. But yeah, great question.
Awesome. And that brings us to the top of the hour. So again, go to this link, scan that QR code. If you think you have a good use case that would really benefit from RFT, we'd love to work on it with you. Feel free to find any of us on LinkedIn. This recording will be posted online in the coming days. And we'll be following up by email also with more resources in these next few days. So thank you so much, everyone, for joining from really across the globe. And stay tuned for our next session. Really appreciate it. And thanks, Arnav and Travis. Take care, everybody.